we may look at those examples and see which of the forces should be zeros. Okay. And now I'm going to give the answer. Okay. So the answer is all those forces are zero. The reason is because based on the second rule, if there are two forces at one joint and are not collinear, both are zero force members. And how to understand that? Note that here actually for rule one, we can call it okay. So here for rule one, we can call it T path. And for rule two, we can call it V path. Okay. So it takes practice to identify T pattern and V pattern from a big truss structure. And also, that first requires us to draw the free body diagram for the entire structure. And we need to represent all the support to be the corresponding reaction forces. Okay. And I'm going to show it afterward. Okay. So if it is T pattern, then the third force that is not collinear with the first two one should be zero. Okay. And if it is a V pattern, then both of the two forces should be zero here. Okay. And it should be noted that here we said that there are two vectors, three vectors at a joint. So that means we are going to also include the potential reaction forces as well as external forces as well. That is the reason why we need to first draw the free body diagram of the entire structure before we identify zero force members. Unless you are super familiar with the truss structure, so solely based on the structure itself, it is pretty easy to make mistakes. Okay. So, and how can we understand the T pattern and V pattern here? And please note that they are pretty closely related to the X pattern that we've been talking about in our problem solving. So here you see that if for X pattern, we have F1, F2, they are collinear. 3, 4, they are collinear here and nothing else. So F1 must equals to F2, F3 must equals to F4. That is actually two equilibriums along the two lines, right? Along the two straight lines here. Okay, so now if, for example, I light F4 equals to 0, okay, or I should say that in general, I light any of the four forces equals to 0, that will be a T pattern here. Okay, then the third force that does not along the line that shared by the first two forces, they should be so the third force have to equals to 0 because nothing else can balance that out. Okay, and if, for example, I simultaneously let F4 and F2 equals to 0, okay, or in more general case, I let two adjacent forces equals to 0. Okay, then that will give me a V pattern. Then the rest of the two forces have to equals to 0 because for both of the two forces, there's nothing else can balance them out. Okay, so now you see that actually both the T pattern and V pattern, they are just the special case of X pattern here. And why there's an X pattern here as well, that is just a special case of equilibrium. Okay, but behind those, it is actually it is actually the sense, or I should say the geometric sense of equilibrium of a truss structure. So get familiar with that. It is pretty important to build a sense of structural engineering. Okay. Okay. So now I'm going to give an example. Okay. Now I have a structure like this, and here I have a here I have a point. I have a force that going downward. Okay. Now find out the zero force members in the structure. Okay. And now you can look at the two rules that we have to identify T patterns and V patterns here. Okay. Pause the video and think about that. Okay. Now I'm going to give the answer. The answer is okay. Okay. In total, we have four zero forces, zero force members here. Okay. And how can we identify that? So first, to draw the free body diagram of this structure. Okay. Actually, if you are super familiar with truss structure, supports, and then drawing free body diagram may not be necessary here. But before we are confident about that, we have to do it for the purpose of practice. Okay. First, you have the structure system. You have the structure system here. And note, by saying that it's a free body diagram, that means we have the entire structure separated, and we should have all forces on it. External force P going downward, as well as reaction forces at the 2 points. And note that for the upper supports there, it is actually a pin, but for the lower one, it is a roller that can move vertically. Okay. So now, and for each of the nodes, and you may look at how many forces are there. Okay. And actually, first thing is that we have a T pattern here, right? We have a T pattern here, and we have a V pattern here, right? Okay. And how about this? This node, it is not a T pattern because we have the 3 bars plus 1 external force. So it is actually an X pattern here. Okay. So for an X pattern here, and you can see that the external P, the external force P is also the internal force in the vertical truss member here. And the two horizontal members, their force, their internal forces are equal, but there's nothing else that we can tell. Okay, so and here actually you have 0 force, so based on the T patterns, you have the 2 0 force members identified, and V pattern, here you have 2 0 force members here identified. And of course, by X pattern, you can further identify another 0 force member here. But I would like to say that it is a secondary here. And as long as you can identify T pattern and V pattern and tell that there are 4 0 force members here, it has already been enough. Okay. Okay, so it is pretty much about method of joint here. Okay, so in this structure we've been talking so in this lecture we've been talking about first we finished the problem solving for this truss structure here by method joint. And we see that the main takeaway is that when you have a truss structure and when you are required to solve the member forces that in all is member forces here, and please note it is all. Okay, and or the forces in most of its members here, and we are first, so we can first draw the free body diagram in test structure and to find out the support for forces here, and then okay, then it is a tedious process here. By looking at the free body diagram, and we started from edge, or started from the truss nodes with no more than 2 unknowns. Okay, then we repeat the particle equilibrium for each of the joint by joint. Okay, until we solved all the unknown member forces here. And note that there is a strategy to choose which are the joints to solve first and which are the joints that we need to solve afterward. So the criteria is always ensure that you have no more than 2 unknowns. Okay, you have the no more than 2 unknowns. So typically we started from the edge of the structure. For example, here it is a joint A or E. And after you solve the members connected to A or E, you will have less unknowns associated with the rest nodes, and you can proceed until you solve the entire structure. Okay. And in the process, we've also been talking about X pattern and further talking about the T pattern and V pattern that related to 0 force members here. Okay, so in the next class, I'm going to do a class demonstration to show you that 0 force member, it is although the force is 0, but it is important to keep for the structure integrity, or that should be the structure stability. So, and right now, to identify 0 force members, it is not only important to build your sense of structure engineering, but also it is good for problem solving here. Okay, so, and one thing that I would like to encourage you to think about that, what is the advantage and the disadvantage with method joints here? Okay, so now if you look at particularly this example, and I like this example a lot because it is pretty typical and involves all the important things that we need to learn. Okay, so if you look at the solution process after you solved all the unknown reaction forces here, and then it is a repeated process for each of the joint. Okay, until you solved all the unknown member forces here. So in other words, although it is a tedious process here, when you are asked to find all the member forces, what you need to do is to solve, repeat the repeat the particle equilibrium for each of the joint, and repeat it joint by joint until you solve all the member forces here. It is relatively more organized, and it is good when you are required to solve for all member forces here. So when it would be the case, it is when you design the truss structure. Okay, if you design the truss structure, we need to know all the member forces, and then we need to choose the appropriate cross section for the truss structure here. Okay, but when it, so what would be the disadvantage here? Okay, and you may pause the video and think about that. Okay, so probably some of you have already realized that that is way too time consuming, right? That is way too time consuming here. If you are required to do that in your exam, and imagining that you, particularly for this truss structure that looks not very complicated, you need to repeat the particle equilibrium for 4 times, right? And what if I have more complex structure in practical engineering? Then it will take even more times, right? Okay, so of course, if we ask to find all the member forces, then taking a long time is understandable because it is essentially essentially a complex problem and takes effort. And what if if it is a big structure, but we only require to find some of the member forces? Okay, in that case, and you will find that metal joint will waste a lot of time and solve a lot of truss members that you are not very interested in. Okay, so in that case, we're going to use another method to solve truss members, that is method of section. Okay, so now we're going to talk about method of section here. Okay, so now we are going to talk about so now we're going to talk about another method to solve truss structures. That is lecture 20, method of sections. Okay, method of sections here. Okay, so so in the previous class we've been talking about how to solve. So in the previous class we've been talking about method joint, and so we've been talking about there's a important disadvantage here, is that when we have a relatively complex structure, but we only care about a few member forces there. Okay, so in that case, it will take a lot of time, but actually we're going to solve a lot of member forces that are not very of our interest. Okay, so in that case, we so method joint will be not very efficient. So that is the reason why we are talking about method section. Okay, so one thing is that when would be the case that we need to evaluate only a few member forces here? It is when, for example, you need to do structure in structuring innovation. Okay, so for example, if you have a big trust structure, say that you have a big trust bridge there, but there's just a few trust members of the bridge that got damaged or damaged by corrosion. Okay, so we need to evaluate the corresponding trust member forces and ensure that they are safe. So in that case, so you only need to solve the member forces associated with the few trust members of your interest, right? Okay, so that is a case. So by looking at that, I'm going to talk about an example. Given that we have such a trust structure supported at A and F, subjected to the two external forces, both at E, and find first zero force members and forces in members city, CF, and yeah. Okay, okay. So now you may pause the video and just think about that a little bit. Okay, so now I'm going to start to address that. Okay, note first the problem is asking us to identify zero force members here. Okay, so to identify zero force members here, of course, we need to draw the free body diagram of the entire structure. Okay, it is also necessary when you are supposed to find the support for forces. Okay. So note that for the free body diagram of an entire structure, it should be first you have the entire structure here, and in addition to that, you should have all the external forces and potential reaction for forces at the location that is supported. And specifically here, it is the support A and F. Okay, given that, you may recall that what we've been talking about in lecture 19, and regarding what are the patterns that we can use to identify zero force members. So okay, now if you look at now if you look at D, there's actually T pattern here, and therefore the vertical bar should be a zero force member here. Okay, so therefore, so the bar DF is actually is the zero force member. Okay, okay. So in practical engineering and for example, in the example that we've been talking about in the previous class. Okay, so actually it has two so it can have four zero force members there. So actually for a structure, it can have only one zero force member or multiple zero force members. Okay, so in our quiz and exam, you will be asked to identify zero force members here, and please make sure that to take it and to practice it. Okay, and then we can go ahead to solve the structure here and record that typically the first step is to solve the unknown reaction for process. Okay, and now we've already have the free body diagram of the entire structure. So we can go ahead to establish the equation of equilibriums of the entire structure, right? Okay, so before we get before we continue here, so I would like to have the dimensions of this structure given. Okay, okay, all the grids are 2 meters here. So and the head is 2 meters as well. Okay, so now it is actually the so now we are going to establish the equation of equilibrium. So for this entire structure, how many equations that we have? Since it is a rigid body here, we have summation of forces along x direction, forces along y direction, and summation of moment, right? Okay, summation of moment about which of the point here, it should be, one idea is that A, right? Because we have the most unknowns, the line of action of the most unknowns crossed A here. Okay, so for summation of forces along x direction, we have positive AX, positive 15 kilonewton here, right? Okay, and for y direction, we have AY, FY, and 24 kilonewton. So since 24 kilonewton is going downward, so it is a negative. Okay, and the moment here. Okay, so now we have we need to look at the free body diagram and see which are the forces that would contribute to the summation moment about A. So here we should have first AX and AY, their line of action directly crossed A, so they do not have any contribution, right? And in addition to that, we have Fy here. What is the distance from the line of action to A? That should be 4 meters, right? Okay. Positive or negative here. Okay, so actually Fy is trying to, so now you can have your pen, one end fixed at A and another end you try to push it along the direction of Fy, or you can imagine that you have a wrench here is actually trying to rotate the nut at A, and you are trying to push it by the force Fy here. It is actually rotating counterclockwise, right? So it should be positive here. And similarly, you can determine here the moment of the 24 kilonewton here. Okay, the distance from E to A the 6 meters here, clockwise. Okay. As well as the horizontal force here. And the distance from its line of action to A, it is the height, the 2 meters. Okay, and again, trying to rotate my structure about A clockwise, so it is negative here. Okay. Okay, now we've already have the 3 equations here, and by solving the 3 equations, we will have AX. It is a 15 kilonewton, but it is going towards the left here. Okay, and if you directly solve that, you're gonna see that it is a negative here. And negative means that the direction is going towards the left here. So for AY, it is also a negative number of 15. Sorry, it is a 19.5 kilonewton. So since it's negative, it will be going down. Okay. And we're also going to have FY here. So it is actually a positive number here, and it is a 43.5 kilonewton here, but it's going towards the upward. Okay. Okay. So now we've already have the structure, the free body diagram of the structure here. Actually, the free body diagram, the structure here, and we established the equation of the entire structure and solve all the unknown reaction forces here. And we can go ahead to illustrate that how we can solve the member forces in CD, CF, and GF here. Okay, and now by seeing that it is a method section, we are going to imagine that we have a knife that cut through this structure, and more specifically, it is a cut the members of our interest. Okay. I'm going to imagine that I have a knife here and cut through this structure. Okay. Actually, it is a cut through the members of our interest. And if you look at the example, we have a member CD, member CF, and member GF. And in free body diagram, they are here. Okay. It is the reason why we created a section that cut through the structure here. Okay. And then what we need to do is that to pick up one part of the structure. Okay. So by the section, it has already cut the structure into 2 parts, right? It has already separated the structure into 2 parts. And now we may pick any of the parts and go ahead to analyze it as a rigid body here. Okay, so now it is so it is so it would be not that different if which parts that you pick up. So you can go ahead to pick up the either the left part or the right part. So the solution process will all be the same. And suppose that we pick up the left part. Okay. Suppose that we pick up this left part and draw the free body diagram that. Okay. Step 2. Cut through members of interest and solve the part. Okay. And note that it is still a force analysis, right? It is a force analysis for the left part. And by saying that it's a force analysis, we need to first to draw the free body diagram, right? Okay, so we need to draw the free body diagram. Okay, we need to draw the free body diagram. For the left part, so we see that we have AX and AY, right? And do we know that? We've already solved that in the first step, right? We need to include those. Those are actually AX with a 15 kilonewton going towards the left. Okay, we need to include the actual direction. And we have AY 19.5 kilonewton going downward, right? Okay, what else here? Note that we actually separated the left part out by cutting through the members CD, CF, and GF. Therefore, seeing that you are cutting through the members, you exposed the corresponding internal forces in the truss members, right? Okay, so we exposed also FCD, FCF, and FGF. Okay. Okay. So now it is a free body diagram that we have. Okay. Now for this part of structure, we need to establish the equation of equilibriums. And how many equations of equilibriums that's available for that? Okay. Similarly to the entire structure, now it is a rigid body model, right? So we have summation of forces along x direction equals 0. Summation of forces along y direction equals 0, and summation of moment about a point, right? Okay, summation of moment about a point. Now, about which point you would like to take the summation moment here? Okay, just look at the free body diagram and see which of the point that you have the line actions of the most unknown forces crossing. That is, okay, you may pause the video and think about that. It is C, right? It is the joint C here because you have a unknown force FCD, FCF, and FGF all crossing that. Okay, now we can go ahead to list the equation of equilibriums. And of course, so here it is it would be helpful if we have the dimensions of the structure denoted here, and remembering from the problem statement, we have the distance from point A to G and from A to B are all 2 meters. Okay, 2 meters. And please also pay particular attention to any force that neither along x nor y. Here it is FCF. Do we know the direction of FCF here? Okay, by looking at this structure, we know that FCF is along the member CF, right? And does it belongs to any right angle triangle? Yes, it is. For example, we see that CF is actually the hypotenuse of the right angle triangle CGF, right? It is a right angled triangle CGF. Okay, therefore, we can denote the direction of the hypotenuse by a small triangle that with the base and head all equals to 2. Okay, with the base and height all equals to 2. Okay, with that, we can go ahead to establish the equation of equilibriums. First, along what do we have along x direction here? We have, okay, first 15 kilonewton here at point A. Okay, and it is a positive or negative here. It should be negative here, right? Because it is going towards the left. And we also have FCD positive, right? Okay. And also the horizontal component of FCF, right? The horizontal component of FCF, and how can we find that? It is by force decomposition. Okay, by force decomposition here, and it can be obtained by you have the magnitude of force times the ratio between the base that corresponding to, actually, in other words, it is actually the side of the small triangle corresponding to the horizontal component 2 divided by square root of the summation of squares and base and head, right? Okay, then positive or negative here. It should be positive here. Okay, so if you have any question regarding the force decomposition, and we must take action to do practice. Otherwise, there's no enough time to do that in exam. Okay, please reach out to me if you feel that it is not straightforward for you to find the force decomposition of FCF. Okay. Okay, and lastly, we also have FGF here equals to 0. Okay, and for y direction, what do we have? We have 19.5 kilonewton, and it is going downwards, so it is a negative here. Okay, what else should also be contributing to the summation of forces along y direction? We have FCF, right? We have FCF. Okay, we have FCF here, and it is going downward, so it should be its no, actually here we are talking about the y component of FCF, so that can be calculated by the ratio between, now it is a height, because the height corresponds to the vertical the direction, right? The height to the hypotenuse. Okay, since it is going downward, so the y component of FCF is going downward, so it is negative here. Okay, that equals 0. Okay, and now what else? Okay, so we should also have actually summation of the moment about K equals 1. Okay, what are the forces that contribute to the summation of the moment about C? Okay, we have actually 15 kilonewton here, and times the distance of from the live action of 15 kilonewton to C. Okay, the distance from the live action of the horizontal force 15 k from the live action of the horizontal force 15 kilonewton to C, and you may pause the video and take it as a practice. That distance is 2 meters. Okay, and positive or negative here. Okay, it should be negative. Okay, clockwise. And we have 19.5 kilonewton, and it is going, okay, times the distance from its live action to point C. Now the distance is, it is also 2 meters. Okay, and positive or negative here. Now it is positive. Okay, it is clockwise. It is counterclockwise. Okay, and what else? So you may think about if FCD or FCF would contribute to the summation of the moment at C. Okay, so the answer is no, because their live action are all across the C. So there's no distance from the point C to their line of actions. And we only have FGF, right? Times the distance from its line of action to point C here. Okay, that distance is actually the same as the distance from the line of action of the 15 kilonewtons to C. That is 2 meters. Okay. Now positive or negative here. Okay, it should be positive. Okay. And it is a counterclockwise here. That equals to 0. Okay, those are the 3 equations that we have here. Okay, by solving the 3 equations, we're going to see that FCF is a negative number. So that is correct. And the magnitude is 27.6 kilonewton. And we have which is a 4 kilonewton, and it is a compression as well. If you solve that, you're going to see that it is a negative 4.5. Okay, so the negative here meaning that it is a compression. So, and FCD, it's gonna be a positive number here, 39.0, and it is a kilonewton here. So, if you find, so you're gonna see that the FCD, it is a positive number, meaning that it is the tension. Okay, okay. So far, we directly solved the member forces in CD, CF, and GF. Okay, if you look at the solution per size, the structure is more complex than the example that we've been talking about in method joint, right? But the solution per size is much shorter here. The reason is because the method section is directly targeted on those members of our interest, and we can directly solve them by only one step, by analyzing the part that we by analyzing the part that with all the member forces of our interest. Okay, so now here's how we perform the method of section here is that okay, it is applicable to the cases that we have a structure, but when we are only interested in a few members here. Okay, so the steps is that again we first draw the free body diagram of the entire structure and find out the unknown reaction forces here. Okay, from the free body diagram entire structure, you can also identify if there's any zero force members. It is required in exams and quizzes, and we also be helpful for your problem solving and establishment of structure engineering sense. Okay, and after that, you imagine that you have a knife cut through the truss members of your interest. Specifically here, it is the members CD, CF, and GF. Okay, because those are members that we are going to solve. Once you cut through the truss members here, we actually separated the truss member into 2 parts. Okay, so now you can pick up any of the parts and establish the equation of equilibriums for that part and solve all the unknown forces exposed. Okay, immediately you are going to have all the unknown forces that you needed here. And sometimes in addition, probably we need to find out some more members. Okay, so in that case, either method section or further method joint for some joints around may be needed to be solved. Okay, so now here is one thing that's pretty important. When you cut through the structure, you expose unknown forces. Okay, at once, how many unknown forces can we expose and address? And you may pause the video and think about that. Okay, Actually, the answer is that no more than 3. Similarly to method of joint, at most for each of joint, we can only deal with the cases that with no more than 2 unknowns. The reason is that for each of the particle, we only have 2 equations of equilibrium. Okay, so for method of section here, okay, for each part of the structure, unless if the part is a particle, as long as it has a dimension associated with it, it is actually a general rigid body. If it is general rigid body, then we have 3 equations. That means we can deal with no more than 3 unknowns. Okay, this is very important to remember. Okay, so for each time, we can only expose no more than 3 unknowns. If we expose more than 3 unknowns, then the number of unknowns will be greater than the number of equations that we have. Okay, so we cannot address that in once. Sometimes you may be asked to find more than 3 forces here. Suppose that in this problem, I also ask you to find the member forces in BC. Okay, in that case, you have a 4 member forces need to be solved. But even in that case, okay, what you need to do is that you first cut through no more than 3 unknowns of interest that is still CD, CF, GF. Okay, and you use the method of section to solve that. After you solved that, you can apply method joint for joint C to obtain the member force in BC here. Okay. Okay. This is actually the method of section here. Okay.